Lesson 5.7. Apply the fundamental theorem of algebra. Ooh, it sounds important. It's very fundamental. So, when you're finding the zeros, how do you know when you've found them all, when you're done with the problem? So today we're going to learn how many zeros there are. The fundamental theorem of algebra says a polynomial function of degree greater than 0 has at least one zero. That's saying, oh, if you have an equation, a polynomial function equals 0, there's a solution. Ooh. The zeros might be imaginary, though. A corollary to this theorem says there is the same number of zeros as there is degree, but you may have the same zero more than once. So that means if it's a cubic, so it's x cubed, you're looking for 3 zeros. It's quadratic, degree of 2, you have 2 zeros. That one, it's quadratic, the degree is 2. It's your highest exponent, degree is 2. You know that it has 2 zeros. Let's try solving by factoring. So let's factor this. What times what makes x squared? What is x and x? What times what makes 9 is 3 and 3. Check it. Outers are 3x. Inners are 3x. 3x and 3x makes the 6x. Since it equals 0, each factor equals 0. So the x plus 3 equals 0, and the other x plus 3 equals 0. Solve them, you get x equals 3. But notice we got that twice. So we have 2 zeros. They're just the same number. So our zeros are negative 3 and negative 3. There's another theorem for today, the complex conjugate theorem. It says if the complex number a plus bi is a 0, then a minus bi is also a 0. So that's saying that complex zeros always come in pairs. Your rational conjugate theorem, same thing, but with square roots. If a plus square root of b is a 0, then a minus square root of b is a 0. So let's find the zeros. Notice the last lesson it was rational zeros. This lesson it's all the zeros, but the process is the same. Start by trying to factor. Nope, can't factor it. So then let's do p's and q's. P's will be factors of the constant term, which is the negative 10. So to get 10, it's 1 times 10 or 2 times 5. So it's 1, 2, 5, and 10. Plus and minus, because I need a positive times a negative to get the negative 10. Q's are factors of the leading coefficient, which in this case would be 1. So all the p's over q's would be 1, 2, 5, and 10, with pluses and minuses, of course. So now let's pick one of these and try it with synthetic division. Now to shorten your picking, you can graph it on your graphing calculator if you have one, and see where an x-intercept is. Appears like an x-intercept might be 1. So we're going to do synthetic division with the 1. Yes, you have to. You can't just look at it and say, ah, it's 1. Done. Drop down the 1. Multiply 1 times 1. We have negative 7 plus 1 is negative 6. Multiply, add, multiply, add. Hey, the remainder is 0. So it is a 0. Now your depressed polynomial is going to be quadratic. We started with cubic. We lost a power, so now he's depressed. That'll be a power of 2, so it's quadratic. So we can factor or use the quadratic formula. I'm going to use the quadratic formula. Factoring, it turns out, as this one's not factorable. So the quadratic formula is negative b plus or minus the square root of b squared minus 4ac over 2a, where this is a, b, c. work it out. Stuff in the square root is -4. Square root of -4 is 2i. Square root of negative is I. Square root of 4 is 2. And then we could split this up to be 6 over 2 and 2 over 2. So 6 over 2 is 3. 2 over 2 is 1i. So all the zeros are the 1 that we started with. So we have 1, 3 plus I, and 3 minus I. Notice we use the depressed polynomial from the synthetic division to find the other two zeros. So you have to do the synthetic division and then use the depressed polynomial to get the other zeros. All right, let's go backwards. Let's write a polynomial function with the given zeros. And I gave you 2 and 4i. If we recall, we had a complex conjugate theorem that essentially said complex zeros come in pairs. So if 4i is a 0, negative 4i is also a 0. So we have 3 zeros. That means we'll end up with a cubic function. The factors are in the form x minus a. Consider if we were solving and we had x minus a, we would go x minus a equals 0, and then x equals a. So now we're going backwards. So it's x minus each of our zeros. So it's x minus 2, x minus 4i, and x minus a negative 4i, or x plus 4i. Need to multiply these together. It's going to be easiest if we multiply the complex conjugates first. So if we do the first, x times x is x squared. Outers are 4i times x. Inners are negative 4i times x. And the last are negative 4i times 4i, which is negative 16i squared. But remember, I squared is negative 1. And also 4ix minus 4ix cancel out. Ooh, cancel out. And negative 16 times negative 1 is just positive 16. Now multiply these together. So we have x times x squared is the x cubed. We have x times 16 is the 16x. Negative 2 times x squared, and negative 2 times 16. Rearrange, and you end up with that. And there you go. You have now solved the problem. You've written a polynomial function with the zeros 2 and 4i, and also negative 4i. Few other things. This is more for if you didn't have a graphing calculator or a calculator at all, and you wanted to narrow down that list of p's and q's for the zeros. Descartes' rule of signs. If f of x is a polynomial function, then the number of positive real zeros is equal to the number of sign changes in f of x, or less by an even number. That less by an even number is for if there are some imaginary zeros, then they come in pairs. And yeah, less by an even number. The number of negative real zeros is equal to the number of sign changes in f of negative x, or less by an even number. Notice the two statements are different only in positive and negative, and f of x and f of negative x. Let's use Descartes' rule of signs to determine the possible number of positive real zeros, negative real zeros, and imaginary zeros for this function. So for the positive real zeros, take the function and count the number of sign changes, such as it goes from a positive 2 to a negative 3. That's one sign change. And it goes from negative 3 to positive 9. That's another sign change. positive 9 to negative 12. It's another sign change. And negative 12 to positive 4. That appears to be 4 sign changes. So we have 4 positive real zeros, or less by an even number. So we're essentially counting down by 2's. So it could be 4 or 2 or 0, positive zeros. 4 because we had 4 sign changes, and then count down by even numbers. So count down by 2's. So 4 or 2 or 0. If it was 5, then we had a 5 or 3 or 1. You just keep counting down by 2's. Negative zeros use g of negative x. So replace all the x's in the function with a negative x and simplify. Negative x to the 4th is positive x. Negative x cubed, though, is negative x cubed, so well, negative times negative is positive. Negative x squared is positive. And then here's a negative times a negative, so that becomes positive. And count the number of sign changes. But wait, they're all positive. There are no sign changes, so there are no negative zeros. Thus, if we were doing p's and q's, and we had to find all the real zeros of this function, we could now eliminate all the negative possibilities. We've cut our number of possibilities in half. So, let's make a table of all the possible positive real zeros, negative real zeros, and imaginary zeros. Since it's to the 4th power here, we know there are 4 total zeros. So if there are 4 positive zeros and no negative zeros, because we know there are no negative zeros, I already have my 4 zeros. So that means there's no imaginary, because I already have 4 positive ones. If there are only 2 positive zeros, I need 2 more zeros to make my total of 4. Well, it can't be negative zeros, so that means they'd have to be imaginary zeros. Or maybe there's no positive zeros and 4 imaginary zeros to have my total of 4 zeros. That's the lesson for today. Have a good day. Remember to ask questions in class if you have any.